the Community Tools for Analysis of NASA Earth Observation System Data in the Cloud webinar. This is Jennifer Brennan. I'm the Communications Lead for the ESDIS project, and I will be hosting today's webinar on behalf of the Earth Science Data Systems program. First, what we'll do is we'll just go over a few webinar logistics. We are running today's webinar in voice over IP mode, so no dial-in has been made available. To ensure the best audio experience, everyone's microphone has been muted. However, you will maintain the capability to unmute your own mics during the Q&A period. In the meanwhile, if you have any questions or you have any issues, please enter those into the Q&A pod located on the lower right-hand side of your screen. This works like a chat. We are recording today's webinar. The recording will be made available on the wiki and via email within a couple of days of completion. Although I'm not certain of the final destination for this file, either Chris Linus or Sarah Lubkin will follow up with email providing this information. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and live demonstrations and an additional 15 minutes for the question and answer period. Our speakers for today are Dr. Anthony Arendt, who is a senior research scientist within the Polar Science Center at the Applied Physics Laboratory. Give me just 1 second. And data science fellow at the eScience Institute. And Dr. Scott Henderson, who is a research scientist within the Department of Earth and Space Sciences and a data science fellow at the eScience Institute, both at the University of Washington. Both Anthony and Scott are heavily involved with efforts to develop open source cloud computing tools for interactive and scalable computing with NASA satellite data as part of the PanGeo project. And so you should be able to see the short summary for today's webinar now and the webinar topics. The first half of today's webinar will focus on an introduction to the PanGeo project and highlight efforts to work with NASA satellite imagery archives on Amazon Web Services. During the second half of today's webinar, our speaker will discuss recent progress in the integration of cloud-centric data catalogs such as the spatio-temporal asset catalogs, excuse me, and cloud-native storage formats for multidimensional data types. Finally, we will wrap up today's presentation by sharing an interactive demo and by discussing approaches to encourage a cultural shift in scientific computation through educational events. After our speakers have finished with their presentations, what we'll do then is we'll move to a final optional set of polling questions, and then generally we'll give these questions about 3 to 4 minutes or so, and then from there we'll transition directly to the Q&A following this polling period. Depending upon the volume of questions that are received, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line, with a hard cutoff of 4:45 p.m. With that, it is my pleasure to introduce today's first speaker, Dr. Anthony Arendt. Anthony, and I'm going to pull up your, there you go, Anthony. All right, perfect.
Great, thanks, Jennifer. I'll just share my screen here. There we go. Can you see that?
Yes.
Well, welcome, everyone. My name is Anthony Arendt. I'm a research scientist at the University of Washington, and I'll be co-presenting today with Scott Henderson. We're here to represent the work of the broader PanGeo project. And the specific effort we're talking about today is in relation to a NASA-funded PanGeo effort that includes this team that I have here on this slide. We have colleagues from the University of Washington and over at NCAR, and we have partners in industry as well, Anaconda and our colleagues over at Element 84. I want to begin by just giving a little bit of context for the technologies that we'll be sharing with you today. As Earth system scientists, we're really entering a new era of complexity in the work that we're doing. And there are 3 components that contribute to that complexity. The first is this sort of deluge of data that is available to us for us to conduct our scientific investigations. Everything from the launch of new satellites to our ability to run very high resolution models gives us a whole set of new data sets to study Earth systems. And we need new tools to be able to work with those large data volumes. The second factor is the realization that the key insights in our research of solving these complex global challenges are really occurring at these intersections between traditional disciplines. And so it really is important for us as researchers to be able to speak each other's language, to be able to share our data sets between various subdomains. The third factor is there is a wealth of new tools available to us now for us to conduct these investigations. So it's no longer sufficient for me to be really skilled in one area of science. I also need to have a lot of deep knowledge in tools such as statistical methods, machine learning. I need to be aware of the technologies around cloud computing and open source software if I'm able to fully take advantage of some of these data sets that are growing in volume. So a quick example of the work I've been doing in my career, looking at, for example, one piece of this puzzle of global environmental change. So I look at sea level rise. I want to answer how much glaciers are contributing to rising sea level. I might want to collect data, radar imagery from, say, the upcoming NISAR mission, which allows me to track the features at the surface of a glacier and calculate the volume of ice that's being contributed into the oceans from, say, the Greenland ice sheet. I may want to combine that with high-resolution land surface models and determine regional water balances and, say, validate that against the gravity recovery and climate experiment. Just that one piece of the puzzle requires me to access large volumes of data, terabytes of data, just to explore that one problem. So this reflects a broader need across the geospatial community, is that we really need new tools for scalable data proximate computing to support these explorations of increasingly large data volumes. These are some well-known graphics that many of us have seen to illustrate the challenges. With the launch of satellites such as NISAR or ISAT-2, we're emerging into this space of hundreds of petabytes of NASA cloud storage. On the right, the CMIC archives, these global climate simulations. As our compute power increases, again, hundreds of petabytes available to us to explore what's happening around the globe. Pangeo is this larger community effort to build community around these scalable tools and to help deploy the technologies around that. We're going to talk about this NASA-focused Pangeo project, and the goals of that are to improve our search and discovery and interactive analysis of NASA datasets in particular. So deploying scalable algorithms that we can co-locate with our datasets in the cloud, rather than this current model of where we're constantly downloading data from one of the distributed active archive centers, or DACs. Let's drill into that just a little bit to explore some of the benefits and challenges of these new ways of working. So our current model, and certainly the way I've worked across my career, is to access some data sets through an application programming interface, or API call, from one of the DACs, downloading the data and doing my pre-processing and analysis. Some of the challenges there can be bottlenecks as the data volumes get higher and higher, waiting for data to be loaded to our local machines. The management of these data gets more challenging. Researchers end up duplicating subsets of data with minor modifications across many different versions. If I want to share what I'm doing with my colleagues, they'll have to go to the DAC, download the same data set, perform the same calculations on their computer. So the reproducibility becomes kind of limited. And the computational power is limited by our laptop or desktop that we have available to us. Now, as we move into this mode, and Scott will tell you a little more detail about these technologies, but for now, what we're trying to do is bring our algorithms and our computational scripts into the cloud, co-located with where the data are stored, where we can take advantage of some of these more powerful data and pre-processing toolkits. Some of the benefits there, we get instant access to the data. There's no waiting for the data to download. We're really democratizing our access to these tools because you'll see that we only require our colleagues to have access to a web browser, and then they can come in and use these Jupyter Hub and Jupyter Notebooks. There's no downloading of data. The scalability of our computational power can go up enormously. We can deploy certain nodes in order to calculate the large volumes of data and then shut those down as needed. We might also be able to take advantage of graphical processing units if we want to do things like machine learning. And a key factor here is that these workflows become much more reproducible. I can share my algorithms with someone else, and then they can reproduce that in a cloud environment. Now, there's challenges to this new way of working that we're well aware of and really working to address those as we go forward. One of the big ones that we hear a lot about in the community is that the cost associated with cloud computing can be very unfamiliar, and it takes time to learn the ins and outs of how we can work in that way. The learning curve for some of these infrastructures is quite high, and so we need simplified ways of deploying these tools. There's very legitimate concerns over whether I should be storing my data in a commercial managed environment rather than a more sharing of public data in a commercial space is something we need to think about. And then our concerns about which of the cloud vendors are we going to use. We don't want to get locked into a certain set of tools where another colleague might be using a different platform. So these are all things that are on our minds as we move forward. The overall goal of what we're doing, though, is to really facilitate us as scientists being able to move away from a model where at the top you see spending majority of our time, 80% is the number a lot of people refer to, preparing data, downloading it, cleaning it, and having very little time for doing the actual science. Instead, we want to be able to spend most of our time thinking about the science and be able to minimize this processing and data cleaning and data access. So I'm going to now pass it over to Scott to continue and share with you a little bit about the technologies that we're working with here.
All right.
I think you're good.
Okay, thanks, Jennifer. So I'll now dive into a bit more details on the underlying architecture to this system that Anthony's given a really nice high-level overview of. So in this slide here, I'm trying to distill the underlying architecture of what we've been working on to set up these Jupyter Hub systems in different commercial clouds. And I recommend starting on the right-hand side of the screen when you're looking at this. And the user interaction is what we're trying to really target here. We want people to have an enjoyable experience when working with large sets of NASA satellite imagery, for example. So that interaction, the user interface we envisioned for that is the Jupyter Notebook. We had a polling question to see kind of who is experienced with Jupyter Notebooks when you logged into the webinar. We'll get maybe half of the folks on the call, but it's a very standard interface for running code and generating what people refer to as computational documents, where you can document your equations, code, run that code, produce outputs, all in the same interface. The key to our cloud infrastructure is that we have this Jupyter server running on Kubernetes. I'm not going to go into a lot of detail on this, but it's a cloud agnostic system for running containers, and I'm happy to talk about that more with folks by email after the presentation if that's of interest. But the main ingredient we have to interact with those cloud infrastructure components are software tools in Python, namely the Xarray and Dask libraries. These libraries allow people to interact with analysis-ready data stored on object storage on the cloud, such as AWS S3. So there are a number of formats we can use for this, which we'll go into in a bit more detail, but that is a very high-level overview of the architecture. Behind the scenes, what's happening with Jupyter Hub is that users are provisioned machines, dedicated isolated machines, when they log in through a web form. So at a minimum, we have a couple machines running a server, and that can expand to hundreds or thousands of machines pretty comfortably. And those machines are pretty cost efficient because everything auto scales back down to that single server if that's the only thing that's running. If no users are using the system, everything can scale. We can also run everything on AWS Spot instances, which is cost efficient if you're familiar with the pricing schemes on AWS. But on a high level here, we're just illustrating that each user has a persistent home directory available to them, and they are launched into a familiar Jupyter interface running in a web browser. So the key extra ingredient, people may have used Jupyter Hub in the past, but what the Pangeo project has done is provided a really simple means to make that Jupyter Hub system really scalable with a Dask computing cluster. So this is the piece that allows people to exceed static provisionment of CPU and RAM and scale adaptively to have more RAM, more CPU cores available to them, depending on the computation that you're trying to run. So Dask Gateway is a project we've used to plug into these deployed Jupyter Hubs that allow people to scale clusters. This helps with security because as administrators of the infrastructure, you're in control over cluster settings, such as who has access, how many resources you can consume, etc. From a user's perspective, the interaction with these clusters is really simple. So if folks have used HPC systems or setting up queues to run computing jobs on HPC systems, it's somewhat of a different, more simplified setup. This is a cell from a Jupyter notebook that's initializing a connection to this distributed cluster. So the user simply has to run this, and you'll see a key line of code here which says adapt minimum 10, maximum 20. That's the number of machines you're requesting for your workflow. And those can scale dynamically based on your computations. So we'll illustrate how that works in a demo in just a few minutes. But right now I just want to overview the pieces coming together in the Pangeo project for infrastructure. Finally, I'll just mention that under this project, we've pooled resources from different federal agencies and with generous credits from cloud providers to set up these prototype environments for scientific users. So we have a website which you can go to, fill out a form to gain access to these systems, but we have identical Jupyter Hubs with Dask Gateway running in the major cloud providers right now. So AWS, US West 2, and Google Cloud, also Azure. Binder Hub is another utility built on top of this Jupyter Hub that allows people to customize their own computational environment with different software packages. And so that is also running, and we'll show that as a hugely helpful tool for running demos to illustrate how this infrastructure and software work. And on top of that infrastructure I've just described, we have the entire suite of scientific Python software, which is a huge, tremendous resource. There's a lot out there. I'm going to identify some key libraries today that we've been working on integrating to make workflows for scientific users very straightforward and simple. Those are circled in green here. But I should say, to a large extent, Jupyter is language agnostic. So there's nothing stopping people from setting up the same systems, for example, using the R language or other languages. And now I want to highlight just what some of these key software tools look like. So Xarray is one of the fundamental libraries that we're using within the Pangeo project because it's very amenable to the types of analyses and data sets we work with as earth scientists. It is a data model for multidimensional data sets where you have coordinates and metadata and observations all contained within a single object. So it's very much like a NetCDF file structure, except we're talking about using data in memory with Python. So we have, often we have multidimensional data sets in earth science, fundamentally 3 key dimensions, latitude, longitude, and time. But you can increase that with, for example, climate model realizations and many other dimensions if need be. So Xarray provides a label-based selection to your data, which is very intuitive for a scientific user. You'll see here, I'm giving an example of, looks like I skipped a slide, excuse me. So this quick example of code demonstrates loading a sea surface temperature dataset from NOAA into an X-ray dataset within the Python programming language. So you can see here a few lines of code, opening sea surface temperature, and if we print out what that data structure looks like, you'll see it's multidimensional with latitude, longitude, a number of bands, and also a time dimension. So we can operate on that data object by labeled indices, which makes X-ray very powerful. Here I'm selecting the sea surface temperature variable and also doing a selection based on a specific timestamp. You can interpolate quite easily. If that timestamp doesn't actually exist in the data set, we'll average the two closest data sets, and you can easily plot results. So it's a great way to interrogate and explore multidimensional data. Finally, for more advanced computations, you have really powerful built-in routines, such as doing grouping and aggregation of this data. So this code block here, which we won't spend a lot of time going over in detail, but once again, you can see kind of an intuitive syntax of grabbing the data set of interest, applying groupings based on months over this multi-decadal data set, taking means, and excuse me, extracting latitude, longitude ranges. In this case, to calculate a sea surface temperature anomaly index over a particular region in the globe. So we're reproducing this figure over here showing El Nino and La Nina periods from NOAA data. Okay, so that workflow of using X-ray is especially simplified on cloud systems if the data sets you're reading are in an analysis-ready format. So there are many different definitions of analysis-ready data. On a fundamental level, we'll argue that it's helpful to just think of this as breaking down whatever your data is into partitions or into chunks. So there are different formats you can use for this. For raster imagery, cloud-optimized GeoTIFF takes a big array and stores it as small subsets of that big array. The ZAR data format is kind of a replacement for NetCDF, where you're taking data variables. Each data variable here in this slide is represented in a folder, and then storing chunks of data as individual files. So this can work on a standard file system. It can also work very well on systems like S3. And then when you're using X-ray, you can read those different chunks of data in parallel or in a distributed fashion, which greatly speeds up analysis. The other component to analysis-ready data from our perspective is a cataloging system that makes things discoverable and easy to ingest into your preferred analysis pipeline. So there's a kind of emerging standard used by many commercial and non-commercial imagery providers called the Spatiotemporal Asset Catalog. It is a very simplified metadata system where you can reference more complicated metadata behind the scenes, but it's really tailored towards users searching for imagery. So it's a GeoJSON format metadata that's meant to simplify user search. So it's emphasizing fields that users typically search for imagery by. Intake is a Python library that we've been working with to facilitate loading in any imagery that has a spatiotemporal asset catalog associated with it into X-ray Python objects. So there's a library we've put together in this project called Intake Stack, which allows for the simplified loading and analysis of data into Python specifically. And here's one example where we'll go over this interactively in a moment, but we import intake library, and we have a function to open a stack item. So this is pointing towards a JSON metadata for a particular Landsat 8 acquisition. And from that metadata, we can load band information directly into a Python object, so streaming into memory without necessarily referencing the exact path to that file set for the user. It's done behind the scenes by crawling the metadata. Ultimately, though, as users, we want to interact by search for geospatial data. So our colleagues at Element 84 have put together a nice API for searching any stat catalog. In this case, I'm highlighting Landsat 8, which is a publicly available data set. We're searching by a bounding box and time, and perhaps some other metadata property. But the key search is always bounding box and time for most use cases. And again, we're able to load not just a single Landsat scene, but an entire catalog that we can browse through graphically. So based on this search, the code here is showing a quick kind of user interface to browse through the various acquisitions available, and the bands, and also metadata about those bands. All right. Kind of the final piece of the puzzle for interactive exploration of data is visualization. And so we want to easily, once we bring that data array into Python, be able to browse graphically a given bands, but the analytical data rather than a pre-generated thumbnail, for example. So for this, we are using the HoloViz set of tools. Again, this is Python specific, built to work well with Xarray so that we can interactively plot in a web browser. I'll give a quick video of this. Hopefully folks can see this video playing where this is that same static image of before. I'm looking at different bands for a particular Landsat acquisition, switching to near infrared, and then I can zoom in on particular regions, and we're going to pipe in the appropriate pixels for that given resolution. So this is key for not crashing your web browser, where you don't want to send all 100 gigabytes of this Landsat stack into the browser, but you want to send the pixels, only the pixels you need for visualization. Future efforts is we're looking into ways to integrate this same kind of pipeline of tools on top of a CMR search. So again, colleagues at Element 84 have prototyped some systems to output a stack response from a CMR search. And given that, we can use this same tooling to load any NASA asset, really. Okay, so we want to spend some time on an interactive demo today. So viewing slides can be kind of boring if you're out there and going through many virtual workshops these days. So in this demo, on a slide here, if you're following along, you can go to gallery.pangeo.io, or if you've opened a link to the actual slides, just click on this link. And what is the Pangeo gallery? So this is a gallery of notebooks. If I go to the main page here, gallery.pangeo.io, these are a collection of notebooks that we've put together to illustrate these tools coming together. If all of this stuff I'm describing is brand new, I highly recommend this tutorial gallery, which we shared at AGU last meeting, which is kind of starting from the basics. But there are some really complicated advanced workflows that are detailed here and accessible to anyone to try. I'm going to go over this Landsat 8 tutorial, which I think is most relevant to NASA satellite imagery. So clicking on this tutorial, you'll notice a few things. This is linked to a GitHub repository. So everything is open on a public repository. And there's a notebook here that you can look at statically. It describes many of the, tools that I've been talking about in the slides. So you can kind of scroll through this and see a rendering of what we're about to do interactively. The really powerful feature of this gallery is that we actually have built in the capability for people to run these examples interactively. So if you click Launch Binder, you'll see a spinning screen here and some notices. launching Binder. So this is provisioning resources on AWS for me to run this notebook in the US West 2 region. Under the folder Landsat 8 tutorial gallery, you'll see a notebook, Landsat 8 IPython notebook. And this is the exact same file we were just looking at rendered. So I want to spend a few minutes now running through this with you. I think that this illustrates a lot of these tools I've talked about in the slide, brings everything together. And importantly, I hope that other folks on the call are running this on their own simultaneously because we have that capability. You can also do this later when you have a bit of free time. So I'm going to go through these cells and not discuss them in great detail, but give a high-level overview of what's going on once again. At first here, again, this system is running in the AWS US West 2 region. So Landsat 8 is a public data set, also hosted in AWS US West 2. So this code, this algorithm, is running next to this data for fast access without the need to download to your local laptop. As a starting place, we're going to run a search. So this is using this Element 84 search tool to look through the stack catalog for Landsat 8 data. We're putting in a bounding box, a time range, and some other properties from Landsat data. This returns a list of 19 Landsat acquisitions. There are lots of libraries in Python for viewing metadata. GeoPandas is one that allows us to look at this return in a tabular format. You'll see each one of these Landsat acquisitions has associated bands with it. We can, for any one of those acquisitions, look at some details about what the bands are, what their common names are, and other properties such as ground sample distance. So this is all contained within the stack metadata. We can use the HoloViz library to, instead of looking at this metadata, which is the polygons really of the ground footprints in tabular format, we might want to look at it in map view. So this is just showing us what our search returns, looking at some Landsat 8 data over Seattle, where Anthony and I are currently at. Jupyter Lab is a very powerful interface for writing code. You have a lot of custom interactivity you can build into this interface. So one example is a simple little tool here to display the thumbnails of everything in this catalog. You can create views for any of the outputs and rearrange your workspace. So I'm going to illustrate here just a quick browsing of the thumbnails with a slider. You can see, here's a good one. Limited clouds, a lot like today in Seattle. So that's all well and good, but what if we want to do some computations with this data set? This is where the intake stack library comes in that I was describing, where we're taking the results of that search and loading them into a catalog. This is all very fast because we're just looking at metadata here, small metadata files. That metadata contains links to the actual images, which are larger in size. But let's say we want this scene. We want to load band 2 and plot it and work with it in Python. It's a very straightforward command to just drill into the catalog and return an X-array data object, which we see here. Again, this is very fast because we're not actually reading any of the data, just the metadata. This data is stored as a tiled geotiff. So when we load any of these bands, we can request a certain chunk structure, which might correspond to the way the files are actually stored on S3 in this case. So you can see by requesting a specific partition of tiling, we have the means to store this as a chunked array that really facilitates distributed workflows. Let's say we want to calculate zonal statistics, where we only want this upper region of the array, or the upper left region. We can extract those chunks rather than the entire file, as we would do up here, where the array is just stored as a single set of pixels. Finally, I'll illustrate that this is an example just for one band, but it's very easy to construct larger data structures. So I've called a function here that we've built into intake stack called stack bands. That's aligning these, well, they're already aligned in this case, just returning all bands for this particular Landsat acquisition. So you can see our total data size is a gigabyte if we were to download it. And we have 8 bands, and the X and Y, which in this case are easting and northing components. We also have metadata returned to us with this X-ray object. So we're keeping track of the coordinate reference system and the grid this data is stored on. So finally, we can store these different bands as data variables in an X-ray data set, so that provides a more convenient way to keep track of what we're looking at. If we want to do band indices, we might not remember what band 4 is. Instead, we can use labels, and so we're keeping track here of things in terms of their labeled index. Finally, computations are triggered based on the requested data. So if I'm only interested in a small subset of eastings, northings, and want to calculate the mean of the near infrared for this particular Landsat acquisition, it's simple to do so and not read the entire file. We can also illustrate here how HoloViews is used to interactively explore this data set. So I'm taking all the bands of this particular acquisition, and I'm able to select different bands. Go to Cirrus or near infrared. And like I showed in the screencast earlier, you have tools over here to interact with this data. You also have interactive output of values. And we can zoom into a coastal area here, and the resolution is going to update based on our zoom level. Finally, I want to show what happens if you start scaling this workflow. So what happens if we use a distributed cluster. So this code cell here is initializing a cluster. Hopefully it doesn't take too long. If it does, I've already run this in another tab. Depending on how many people are using this system, it can definitely take a while for this cell to run because you're launching machines in the background. So we'll come back to this in just a minute to see if it has launched. Generally, it takes a minute or two. Again, it depends on how many people are using this simultaneously. But I'm going to scroll down here to this one that I ran just before the workshop. So what happens once your cluster becomes active is you get a view here into the number of workers on the system, the amount of your distributed memory, and also an interactive dashboard for viewing information about the cluster as it's running computations. You can also display that dashboard within the same notebook. So that's what I've done here with this task tab. I have a task stream showing what happens when this cluster is running with the data set. And this next code cell is taking all of the Landsat scenes for our search and compiling them into a larger X-ray data set. So now we have a total of 77 gigabytes if we were to try and download all of this to our laptop in one go. But we're only using the metadata again. So this is multidimensional. We have 19 timestamps, or 19 acquisitions, and then our X and Y dimensions. And when we run distributed computations, there's nothing very special that we need to do. Xarray, because it's connected with Dask, is going to automatically farm out these computations based on the chunks of the array that we set when we loaded the data. So what this looks like is if we were to calculate NDVI index, we can use the labels to select different bands, and then output what that data set would look like. In this case, we've reduced the amount of information greatly because we're doing one index per date in this case. And so we can then run a computation. Persist is going to put this data set in the distributed memory of our cluster so that we can work with it really efficiently and browse through with a time slider, and again, get interactive outputs on the NDVI for different dates. I'm going to hop back here. So you can see it took a few minutes there for me to launch a cluster in this case. I'm just going to illustrate how to open this dashboard. I copy a link to this dashboard and open this Dask tool, should be able to connect to it. You have available all kinds of diagnostic streams for the cluster. And when you run computations using the cluster, this task stream should light up in terms of showing activity, what's going on. Again, there might be a bit of delay, but you should start to see kind of the task stream flowing, and more bars are going to show up as more machines are connected in the background. So if I look back up here at our cluster, we've gone up in memory temporarily, and then things can scale back down. So that's pretty neat. It's 33 seconds to construct this 78 gigabyte array because we're only using metadata. Similarly, you can kind of preview calculations because the calculations aren't done until you explicitly say compute on anything or plot something. So this is what the computation looks like as it's running. The final kind of illustrations here are just plotting a small subset again, and then maybe saving just that subset as a netcdf file locally for future use. This is a really common workflow where you want to work with large amounts of data, but don't necessarily want to store it all. You're only interested in a small subset or the final image or figure in your calculation. And so you could download this netcdf file for a particular subset, which is just a very small couple megabyte array, and shut down the system and log off. So I'm going to go to log out now that I'm done. Or if you just close these browser tabs, everything shuts down. And I will turn it back over to Anthony to finish things off in the presentation.
That's great. Thank you, Scott. I'll just speak for a few more minutes about some of our efforts to help bring some of these tools out to the broader community. Just looping back to the overall purpose of the Pangeo project, this is actually a quote from the website. Pangeo is first and foremost a community promoting open, reproducible, and scalable science. And so we are doing everything that we can to help integrate these tools into scientific workflows. We can spend a lot of time building these technologies, but if people don't have an opportunity to take the time to learn them and to work together in a collaborative environment, then we might not get full adoption of all of the great things that Scott just shared with you. So one of the ways that we're addressing this is to take advantage of an educational and workshop model that comes out of my colleagues at the eScience Institute. This is what we're calling a Hack Week. Started a little over 10 years ago. We've now run Hack Weeks for all different kinds of domain science, from neuroscience to astrophysics to, in our case, a lot of earth science applications. All of these Hack Weeks share this kind of model where we create a really welcoming learning environment where people can work together to build and collaborate on building open source software. These Hack Weeks generally involve community building activities, hands-on tutorials. So we'll often start the day with some interactive tutorials, and then later on people shift into working together on projects and hacking in small project groups. We really emphasize peer-to-peer learning, and people really benefit from the fact that we gather together a lot of different perspectives, a lot of expertise in the room to help us share ideas and move people forward in adopting some of these tools. Now, building these kinds of communities when we're not able to meet in person is certainly a challenge. What we've done recently is explore some ways that we can leverage virtual tools to still create these kind of atmospheres where we can do this kind of work collaboratively. The recent example of that is our second ISAT2 Hack Week that occurred back in June. Scott was part of that, along with many of my colleagues in cryospheric science and data science. We had about 80 or so participants. We used Zoom and Slack and other technologies, and we found that people were able to build collaborative toolkits, work together in small teams, despite some of the challenges of working virtually. And importantly, through this Hack Week, we've actually started to build an open source library called IcePix that is now continuing to be developed, but really came out of these that probably wouldn't have occurred had we not brought people together in these collaborative atmospheres where we can start to design software together. Pangeo is a key infrastructure for us to do these kinds of events. It allows us to deploy these custom toolkits where everyone has access to them. We don't have to spend any time worrying about deploying libraries on people's local machines. A user can come in through a GitHub authentication and get access to one of these machines in the cloud, which is then linked to a common file system. So we have these Jupyter Hubs that can be provisioned for any of our existing Hack Weeks that we're running. We're getting a better idea of the cost of these, and we can start to scale this out to other events. One of the key features of this that we've made some progress on within this project is to simplify the way that we deploy these Pangeo architectures. We're taking advantage of tools like Terraform, which allow us to script up the workflows for deployment. So it's an infrastructure as code type of architecture, so that we can really customize this, not spend a lot of time going in and creating these custom environments. We can actually just create a script for each one and deploy them and tear them down really quickly for each event. So I'll just wrap up with pulling together the lessons learned throughout this project that we'd like to leave you with as we finish the presentation. The first is that as we transition to hosting more of our data in a cloud environment, an essential step, we think, is to take that a little bit further and think about providing these data sets in a cloud optimized format. When we have data prepared in that way with the different chunk sizes that we can then plug into these different computing nodes, that will allow us to take advantage of all of these architectures and scalable computing toolkits that Scott just described. When it comes to developing new computational solutions, we really encourage people to consider open source tools as a starting point. It allows us to avoid reinventing the wheel, and then we can plug into this larger ecosystem that allows us to kind of have a cascading effect of the benefits that we bring to one library can then impact all the different concentric circles that you see in this sort of Python ecosystem. As we think about infusion and interoperability, we really believe that it's important to adopt consistent community standards. So things like the stat catalogs that Scott mentioned, these community-wide agreements on how we provision metadata and access the data will allow us all to more quickly build common tools around these products. Education and outreach is really vital for us to shift our community in these directions, and we're really interested in working with people on this call. If you would like to explore how we can bring these tools to your communities, we'd love to talk to you about that. And then finally, we really believe that these tools will have clear benefits for our research communities. And we're aware that it's important to think about and help researchers answer the question as to what the funding model for that is going to look like in the future, so that we can bring more of these tools and have greater adoption of Jupyter Hub and Binder toolkits, and begin to design strategies for how these can be supported in the long term. We want to just quickly acknowledge all the different funding streams that have brought this work together, not just the NASA work in specifically, but the broader Pangeo ecosystem has been supported by many agencies and industry groups as well. And I'll finish with this slide, just in the spirit of open source software. We really encourage all of you who are interested in learning more or would like to contribute to Pangeo in any way. You can connect with us through our GitHub website, through Discourse, through Twitter, in many different ways for you to engage with us, and we'd be happy to answer any of your questions in the time that remains. So thank you very much.
Okay, thank you, Scott, and thank you, Anthony. At this point, we will transition to the optional final set of polls. We'll give these 3 to 4 minutes or so, and then from there, we'll transition to the Q&A period. Okay, everybody, at this point, let's transition to the question and answer period. For those of you who asked about the presentation, you should see below the question slide, there is a link sharing pod, and if you highlight the title of the presentation, you should be prompted with an option to browse directly to the presentation for today. All right, let's see if we have any questions here. Okay, the first question is, give me just one moment. Can you guys hear me okay? How do archive formats fit into the Pangeo ecosystem? For example, NetCDF, HDF, if there is hesitancy to convert golden granules to new formats.
So I'll jump in and start by saying that Xarray, which I demoed, was really started from reading NetCDF and HDF files. So a lot of the functionality we demonstrated today works perfectly fine with HDF files on disk. You tend to start getting performance issues if you just read exactly the same HDF file from S3 bucket. So I think it comes down to whether or not you want to start enabling high performance. There's nothing wrong per se with the standard HDF format. You just start getting into performance limitations compared to others if you're doing a direct copy into a system like S3.
Okay, thank you. The next question is, in my experience, it is very easy when working with large data sets to create tasks that repeatedly run out of memory in Dask. What are your suggestions for debugging this issue?
Scott may know more about that one as well.
Sure. I suppose, so the intention of Dask is to eliminate exactly the problem you're describing. So, it's unfortunate when you run into memory problems with Dask. Of course, all systems have their bugs and issues. Being an open source project, one of the great things about it is there's the GitHub issue tracker for the Dask library. And so the key is really constructing some sort of minimal example that you can share on a platform like GitHub such that this community of people using Dask can help troubleshoot what's going on specifically for that case.
Okay, thank you. And I think we did get taking a look through here. Here we go. Is there a way to determine how much we are costing you?
I think that's in reference to running the Landsat 8 example. I'm not actually sure.
Byron, is that right? Yes.
So on the order of maybe $1 per person to run that example. The key thing is that everything is running adaptively. So as long as you run that notebook, kind of look at the results for a bit and then shut it down, yeah, on the order of, I would say, $1.
And our ability to monitor costs keeps getting better. There are more sophisticated dashboards for determining costs, and in part, some of the advancements in this project with Dask Gateway are enabling us to protect what we're deploying from, one user coming in and deploying massive amounts of scaled up computing. So that was a problem earlier in the project, that we're getting more and more tools to be able to manage that carefully.
Okay, the next question is, how do you determine the appropriate chunking when creating a ZAR file from its original format, and what workflows or tools do you use to process the data?
The chunking kind of often depends on the use case. So if you're partitioning out in time or by a certain variable, your chunking strategy might change accordingly. And there are guidelines around sort of maximum chunk sizes that are optimized for interaction with Dask. But it's still a fairly new tool, and sometimes requires just some experimentation based on your particular use case. Scott, did you want to say anything additional?
Yeah, just that for starters, having a chunk size is helpful. I think there's just so much geospatial data out there that's stored as a flat set of pixel values. And so there are, of course, optimizations, like Anthony's saying. If you're doing time series, you want to compile all your time pixels in the same pixels from different times in the same chunk, versus if you're doing a spatial analysis, the opposite would be true, where you're putting more emphasis on the spatial groupings of pixels. So this is a huge kind of issue because it's so central to many analysis workflows. I'm not sure if we can share a link, but there is a lot of enthusiasm over a new project that folks on Pangeo are working on, a library called Rechunker, which is this system set up to temporarily kind of convert your data set into a different chunk structure for a given analysis. So this would be stored in a temporary fashion, let's say if you want to do a efficient time series analysis of Landsat data. But that does require some sort of transformation.
Okay, thank you. And then as a follow-up before we get to the next question, you mentioned, where are the guidelines you mentioned?
Guidelines for setting up chunks on a data set?
Yes, that's it.
So I'm not sure if we can share links, but the Dask library documentation has a section on chunk size considerations. There are a few kind of places where you could find information about this, but that's the documentation for the Dask library is where I would begin searching for chunk size.
Okay, thank you. And then the next question here is, what can authorization systems like Earth Data Login do to improve this interactive experience? Are they working fine for your purposes so far?
Scott, do you know, I don't think that's a bottleneck from our side. It's certainly with the ISAT2 data, it's just been integrated into some of the library development where it's just a little more seamless. It still requires a user to have a login, but I don't know much more than that.
Yeah, I would say, just as a concrete example, for the ISAT2 Hack Week, we had all participants set up an Earth Data login before the event, and many of the tutorials had people interactively enter those credentials in order to download data sets from NSIDC. So that was totally seamless for that purpose. I think there are potentially some limitations for doing a workflow like we just illustrated with Landsat. The reason that makes such a great tutorial is it doesn't require authentication, right? You're reading a public data set, which AWS is hosting in their public datasets program. To read those files, you don't have to enter credentials, and that's a huge convenience because then you don't have to worry about people compromising their credentials on kind of web-based infrastructure. So I think something to consider for folks who are setting up infrastructure, of course, is that is a potential bottleneck for workflows to read into the data sets of interest that you're wanting to share with people.
Okay, our next question is, have you run into any issues using a shared file system during hackathons, such as users accidentally overwriting or deleting one another's files?
So this definitely came up when we were setting up the ISAT2 Hack Week. Right now, user home directories are completely isolated, so there's no risk of users interfering with each other's home directories. But we did create a shared directory and just gave everyone complete read-write access to that directory. So it was very convenient for moving data sets around and sharing information. But there was the potential for users overwriting each other's information. This is all configurable at the infrastructure level. So if you're familiar with setting up file system permissions, there are solutions to create directories that are accessible by everyone but are not writable, for example, by everyone.
Okay, thank you for your response, Scott. Are there any additional questions? Just looking through. Any additional questions? If not, I would like to thank our speakers today and thank all of you for participating. And again, I will make the recording available. I'll send that both to Chris Linus and also to Sarah Lubkin, along with an MP4 output, along with a direct link today. Anything further? Just looking through. I don't see anything. With that, Anthony or Scott, any final remarks?
No, I don't think so. Thank you very much for this opportunity, and we'd be happy to connect with anyone afterwards, either on email or any other channels.
Yeah, thanks.
Okay.
Thanks everyone for attending, and thanks Jennifer for organizing.
Absolutely. All right, with that, we will log off from today's webinar and be looking for an email with the recording files. All right, thanks everybody.
All right, bye.
Goodbye. See ya. Bye-bye.